Hi, this is Mrs. Cribb, and we are going to begin the honors notes for Chapter 13. So pull out your notes, please, and follow along. You'll also need your reference charts, and so I may be referring to those periodically. So chemical bonds store energy. We know that's true because when we eat food, we eat it so we can have that energy. And when the bonds are broken, that stored up energy, it gets released. Bonds are broken through vibration. The strength of a bond between two atoms depends on the elements and that are bonding and on the length of the bond. And bonded atoms are more stable than unbonded atoms. And we had way back when kind of an energy chart about that, but where we had two atoms and there's their energy on this side, and then when they bond, their energy went down like this, down to here. So maybe that was A and that was A, and this was A2. That in a bonding orbital, the energy was lower and that makes them more stable. So let's see here. Bond breaking is always, energy is always required to break bonds. Kind of think of people holding hands, that's the bond, and think of Red Rover running through those hands. You're breaking those bonds apart. So you always have to put in some energy to break something apart, and bond breaking is thus always endothermic. So there's two parts of this, the breaking part and the making part. So bond breaking is the first part, and it's always endothermic. And bond forming bonds is always exothermic. So there's the two parts, okay? And somehow we got to get both of these. Bond breaking, endothermic. Bond making, exothermic. Because when we make a bond, we're trying to go down. See, we made a bond, we go down in energy, we got to let go of that extra energy. That's the exothermic part of it. The stronger the bond, the more energy is released. So the stronger this bond right here, the lower this would be on the chart for energy. So this is, remember, this is energy on this side in joules, and this is atom A and atom B. A reaction that breaks strong bonds and forms weak ones requires energy. Now remember, bond breaking is endothermic. We always have to put energy in to break it apart. And bond making is always exothermic. We always get rid of some energy to make bonds. So we just have to compare. Think about it. Forming strong bonds releases a lot of energy and requires a lot back to break them. Weak bonds release a small amount of energy, so only requires a small amount to break them. So if we go from a strong bond, which takes a lot of energy to break, and we form weak bonds, it only releases a little bit of energy. So that means it took more energy on this side, so that this is going to be an endothermic reaction. If we go from a strong bond to a weak bond, it's endothermic. A reaction that breaks weak bonds and forms strong ones releases energy. It's opposite of that. Think about that. Weak bonds release small amount of energies and thus require small amounts to break them. Strong bonds release a large amount of energy. So if we're going to go from a weaker bond that releases a tiny bit of energy out, let's do a little arrow out, okay? And we're going to make strong bonds. Strong bonds release a lot of energy. We're going to break weak bonds. That means a little bit of energy in. We're breaking the bonds. There we go. And we're going to release a lot of energy when we create strong bonds. So here we let go of way more energy than we took in. So we have a negative delta H, a negative change in the heat. And so it's an exothermic reaction. Okay, now there's a figure you can look at in your textbook. So let me see if I can pull that up for you. Okay, so I drew the picture for you right here. And this is from figure 1312 in your textbook. This is the first picture. So this one is showing you breaking reactants that are strong. They have low amount of energy. Like this over here might be kilojoules or joules. So they have a low amount of energy to begin with. That means they're a strong bond. It doesn't take a lot of energy to keep them together. So I have to put in, since they're a strong bond, I have to put a lot of energy in to break them. And they form products up here, and these products are weak because it takes a lot of energy to keep them together. So the delta H we calculated is that sum of the products, sum of the heat of the products minus the sum of the heat of the reactants, and it ends up being a big number minus a small number, which is a positive delta H. And this is an unfavorable situation. It's chemically unfavorable. It does happen, but it's not favorable. Then the other picture is very similar, so let me draw that one for you. All right, so you may have pause the videos to copy these, but this is the same kind. Now this one with the positive delta H, this is the endothermic reaction, and this is an exothermic reaction. And here we have reactants that have, remember this is energy on this side, the reactants have a lot of energy in them. So that means it takes a lot of energy to keep them as reactants. The products only requires a small amount of energy, a smaller number. So the less energy that's required, the easier, the more stable it is. That's the word stable. So the delta H again, the heat change in the heat of the reaction is the sum of the products minus the sum of the reactants. The heat of the products minus the heat of the reactants. In this case, the product number is small and the reactant number is big. So a small number minus big number gives you a negative delta H, a negative change in heat. That's an exothermic reaction, and it is favorable. This is a favorable situation. So copy these two graphs down in your notes, and then when you're finished, move on. Okay, in most cases, exothermic processes are thermodynamically favorable. That means they're more likely to happen, and endothermic processes are thermodynamically unfavorable. But there's other things that happens. Endothermic reactions happen all the time, though, like melting ice. That's endothermic. Those cold packs where you break the seal and you have a chemical reaction, it feels cold, so it's endothermic. So determining whether something is endothermic or exothermic is needed. Determining more than if it's endothermic or exothermic is needed to figure out if it's going to happen spontaneously. So there's other factors involved, and we're going to start to learn about those. Chemical processes tend to proceed naturally in the direction that increases disorder. We want to increase disorder or spreading out of the energy of the system. The second law of thermodynamics relates this when it says the natural processes decrease the order found in the universe. It spreads out energy throughout the universe. So which has more order? Gas, liquids, or solids? Well, solids have the most order. Think about it. Molecules, think about how the molecules move, and the solids are very, they're kind of vibrating in place. Entropy, and we use the letter S for entropy, and I like to write disorder to help us remember that the letter S stands for entropy, is a measure of randomness or lack of orderliness in a system. Disorder. It is a measure of the dispersal of energy in a system. That's important. That's kind of an updated for this year. A dispersal of energy in a system. In natural processes, energy tends to spread out, not concentrate. A hot pan cooling off on a stove is an example of entropy in action. The heat is leaving the pan and heating up the surrounding air, and giving the air more energy and more randomness. So it's increasing the disorder of the surrounding system by giving it more heat energy, more vibration. So which has more entropy? Again, look, gas particles solids are very close, and vibrating liquids are moving around a little bit more, but gases are flying around. So gases have the largest amount of energy, the largest amount of entropy rather. Entropy, which is disorder. So this is the most and the least entropy. The most orderly is the least entropy. All right, the entropy of a substance increases with temperature because look at here. It has to get hotter from here to here, and then from here to here. So the temperature is going up. My kinetic energy is increasing. I'm increasing the movement of all the particles. At absolute zero, theoretically, all random movement of particles or atoms stops, and the entropy is zero. S would equal zero at absolute zero. But that's a theoretical position. Now we're going to calculate entropy just like we did enthalpy. It's delta A, this is the summation again. The summation of the change in entropy is equal to the sum of the entropy of the products minus the entropy of the reactants. So the delta H was the sum of the heat of the products minus the sum of the heat of the reactants. And this is the same thing. Any delta is the second thing minus the first thing. And this still works because you normally have reactants on the left and you have products on the right. And this is the first thing, and then it forms new things, which is the second thing. So changes are always the second one minus the first one, just like delta T is the final one minus the initial one, or the second one minus the first one. Same thing with delta H and delta S. A reaction with positive delta S increases disorder. So a positive delta S is a good thing as far as spontaneity goes. It's spontaneous. It increases disorder, energy, and temperature. The products have more entropy than the reactants. A reaction, typo, with a negative delta S decreases disorder. So a negative delta S means it's actually getting more orderly. More orderly. And so that's kind of not spontaneous. Not spontaneous. So let's look at this reaction. Does the reaction of ammonia plus hydrochloric acid that yields ammonium chloride produce an increase or decrease in entropy? Now we can do this more than one way. We're going to figure it out. First of all, I want to think about it without doing any math, and then we'll do some math, okay? So here we have, on this side, on the reactant side, we have a gas and another gas. They have a lot of entropy, a lot of disorder. And then on the product side, we have a solid. That has a little bit of disorder. So, am I increasing entropy or decreasing entropy when I take these two gases and I form a solid? Well, both the gases have more entropy than the solid. So I'm going to be decreasing. I should be decreasing the entropy in this case. So there's a way of doing this, though, by calculating it. And I'm going to go ahead and calculate it. What I'm doing now is I'm going to look up the the entropy values out of that big chart that I gave you. So just 1 second here. All right, so I went and looked at the large chart, the two-sided chart that has, on one side it says page 353, and then on the other side it says page 352. So this is from your textbook, and you can get these charts there, and it lists, on those charts, it lists the delta H of formation. It lists next to that the S, the entropy value, and delta G, which we're going to cover soon, that's Gibbs free energy. So I got these three values from that chart, looking under the column that says delta, that says the S. And remember that this little degree symbol means at standard state. So now I'm going to use this formula. I'm going to calculate the change in entropy, this right here, by taking the entropy of the products. Now here's the two products. We have, here's the product. So the entropy of the product. So that's this one. And I have 1 mole of it right there. We have to put the mole. So 1 mole, and it's a summation, so we're going to add it together. 1 mole times, and this is the value, 94.6. And there's the units. This unit right here is used over and over again. Joules per mole times Kelvin. So this is the summation of the products. And since there's only one product, I don't have to add a bunch of junk together. Minus the reactant side. On the reactant, I also have 1 mole of ammonia, and it's times 192.8 joules per mole times Kelvin, plus, because of the summation, I have to add in the second reactant, 1 mole for the HCl, which is 186.9 joules per mole times Kelvin. Now you do have to put the 1 mole in there, because when you have a balanced equation, sometimes Remember the coefficients in the front, they represent how many moles, and sometimes you have more than one. So now moles cancel for everything, all the way across the board, and we end up joules per Kelvin. And that's what our answer will be, because my kelvins are not going to cancel this time. And so it's going to be 94.6 joules over kelvins minus what's ever inside these brackets. All right. So let me do that real quick. All right, so I did that, and you see we're adding those two together. Now I have to subtract those two. And when I subtract those two, I get a negative 285.1 joules per Kelvin. So the change in entropy, the change in S, the disorder decreases. Okay? Now, does that make sense? The disorder goes down, decreases. Well, we made a solid, so the order increased. When order increases, disorder decreases. So here, this shows you that disorder decreased, which means order increased. But delta S is a measure of disorder. So the entropy went down. Now let's do the next one. All processes increase the entropy of the universe. A positive delta S means a reaction is more favorable. A negative delta S goes against this tendency and attempts to decrease entropy. And that's what's happened here. We attempt to decrease entropy. Two tendencies drive reactions: in decreasing enthalpy, which is heat. Remember that enthalpy is the heat. And increasing entropy, which is the disorder. Okay? Now there are four possible combinations, and I'm going to write these four possible combinations in here. So stop the video if you need to, and write them in. So you have a combination of the heat on this side and the entropy on this side. And you can have a decrease in heat and an increase in entropy, a decrease in heat and a decrease in entropy, an increase in heat and an increase in entropy, or an increase in heat and a decrease in entropy. And when you combine all these guys together, you get something called Gibbs free energy. And so we're going to do Gibbs free energy calculations next in the next video. So this is where I'm going to stop.